The following video deals with longboard wheels. The wheels are attached to the board via trucks and can be removed by removing one bolt. There are many factors on the speed of a skateboard wheel. A few of them include the durometer, the size of the core, the width of the wheel, and the size of the wheel. That's the measurement we're concerned with, the size, and how it affects rider speed. One popular aspect of skateboarding is seeing how fast you can go on a run. Two friends decide to set up a speed trap at the bottom of a run and both try to hit 40 miles per hour. Because they have different wheel sizes, they recognize that they're going to need to have different initial heights in order to achieve the same speed at the same spot. However, they don't know how much different the two riders' height needs to be. In order to figure out this difference, they use conservation of energy in both linear and rotational kinetic and potential energy in order to solve the issue. Because energy will be conserved from the top to the bottom, we can set the two equal and see the change in the components of kinetic energy over the course of the run. The accuracy of these calculations will largely be not particularly great, due to the changes in pavement surface, material deformation due to the softness of the wheels, and frictional losses that'll differ based on the two different wheels. However, this should still give us a general estimate of why having a smaller wheel will generally allow you to go faster. Here are the energies involved in the equation. There's both potential energy and kinetic energy initially, potential energy and kinetic energy at the final at the bottom of the hill. The potential energy, because there's zero kinetic at the start, is equivalent to the kinetic energy of the center of mass of the system plus the rotational kinetic energy. Because they're both trying to reach the same final speed of 40 miles an hour, which is equivalent to 17.878 meters per second, and we're going to assume that the mass is roughly 60 kilograms, which is fairly traditional of a light rider, we can then calculate the height based on these equations. We know, therefore, that the potential energy, which is mass times gravity times height, is equivalent to 1/2 mv squared, which is kinetic energy of center of mass, plus kinetic energy rotational. Therefore, the height is 1/2 mass times velocity squared plus kinetic energy rotational divided by mass times gravity. When we run these calculations with these numbers, we get that the height equals 16.291 meters plus whatever the kinetic energy of rotation of the wheels is over 588.6. Let's see how that varies for two different wheels. Here's a comparison of the larger wheel, which is the one I have here, which is 70 millimeters in outer diameter, and the smaller wheel, probably closer to around 50 millimeters, more traditional of a small skateboard. Additionally, the thickness of the urethane, which is this part, of a smaller wheel is generally larger. So we've taken the inside radius for that wheel to be 0.025 meters, and the outside radius to be 0.05 meters. We can calculate angular velocity by converting linear velocity into angular velocity using the distance traveled per revolution, which can be found using the circumference, which is pi times the diameter, 0.07 meters, which is 70 millimeters again, times 2 pi radians over 1 revolution, which gives us the angular velocity in radians per second. The moment of inertia can be found using the equation for a thick cylinder, which is 1/2 mass times inner radius plus outer radius, each of the radiuses squared. So we have 1/2 mass, inner radius, outer radius, and that gives us a moment of inertia. That's for this wheel using an electronic scale. For a smaller wheel, we made up some numbers based on the average skateboard wheel, so we found it to be a much lighter mass of 0.0907 kilograms as opposed to 0.18, and inner and outer radiuses. Kinetic energy of rotation is equivalent to 1/2 the inertia times the velocity squared, equals 1/2 I W squared. And we found the number of joules of kinetic rotational energy you'd have at 40 miles an hour for each wheel, multiplied by 4 wheels on a skateboard, and we get a final kinetic rotational energy for each value. Now that we know those rotational energies, we can plug them back into the equation we had before from height. We know the original height plus rotational energy divided by 588.6, 379.064, that gives us a height of 16.935 meters. For the smaller wheel, we have a height of 16.291 plus 145.096 over 588.6, which gives us a final height of 16.537 meters. Now, this difference in heights is useful, but the real difference will be how far the person has to travel. So, if we're assuming that our hill is roughly a 15-degree incline and remains steady over the whole range, we can find that the length of this side is going to be equivalent to the height divided by the sine of the angle. So, our length for the smaller wheel is 63.894 meters, and for the larger wheel is 65.432 meters. If we find the difference in length traveled, we have 65.432 meters minus 63.894 meters is 1.537 meters. And that's our final difference. So, in order to both reach that 40 mile an hour speed, the rider of the bigger wheels, these wheels, would have to start 1.537 meters up the hill, which doesn't sound like a huge difference, but if it was a race, could mean the difference between winning and losing. And there we go.